And I just apologize. I'm a little bit behind on uploading the videos on YouTube because a couple of videos were corrupted, but I was able to recover them. And then by this weekend, I will upload all the remaining lectures. That way you will have all the content on the channel. The other thing that I want to tell you is I have just uploaded a quadcopter simulation.rar file in Canvas. So if you are on Canvas, please download that file. That file has all the equations that we are going to use, MATLAB simulators, and then we can actually run simple simulations on quadcopter dynamics and validate PID and PD and other types of control. In today's class, my objective is from first principles derive the equation for quadcopters. Before I start, any questions from anyone? Any questions? So I'm going to start deriving, and please note these equations, this derivation is also uploaded on Canvas. Just in case if I make mistakes in deriving some equations, you have the equations as reference. So in today's class, we are going to derive the quadcopter equations of motion. So quadcopter equations of motion. Now it is super important that we start with a coordinate system. Our coordinate system is north, east, down. Everyone comfortable with north, east, down coordinate system? So we have north, east, down coordinate system. And we are assuming the earth to be flat. And we have north, we have east, and we have down. North, east, down. Then what we have is we have our quadcopter. This is the quadcopter. And this quadcopter also has its own coordinate system. So north, east, down. This is the Earth center coordinate frame. So Earth center coordinate frame. And this is aircraft body coordinate frame. Body coordinate. And you have X, Y, and Z in the inertial coordinate frame, which is same as this frame is also called as inertial coordinate frame. X, Y, Z are the positions in inertial frame. X dot, Y dot, Z dot are the velocities in inertial frame. Now, this Earth center, Earth fixed frame and the aircraft body coordinate frame, they are related by three rotations, three successive rotations. The first rotation is roll. Actually, yeah, first rotation, yaw. Then you have pitch, and then you have roll. So basically, from you have Z, Y, X. So these are the Euler angles, or this is the rotation. These are the rotations that would take the Earth center, Earth fixed frame to aircraft body coordinate frames. In the last class and the class before, we derived the kinematic equations of motion. Now, kinematic equations of motion, they are free from mass and inertial properties. But before I do that, I just want to add some more coordinate frame, or just some more reference. So if this is the x-axis of the aircraft, this is the y-axis of the aircraft, this is the z-axis of the aircraft, then I have PQR. So the angular, so we have P Q, not coming on screen. Okay, so X, Y, Z, so P, Q, and R. So those are the angular rates. So I will show it to you here. So this is the aircraft body coordinate frame. This is the x-axis. This is the y-axis. This is the z-axis. So there is P, Q, and R. Now these are the angular rates. Now I would emphasize this significance of body angular rates, because think about it. If on this quadcopter you have an IMU, and that is going to be the topic of our next chapter. So you have an IMU that has 3-axis accelerometer and 3-axis gyroscopes. So what would that IMU give us? IMU will give us the body rates and the body accelerations. You can differentiate, you can integrate the body accelerations twice, and you can find out the body positions. You can integrate the body angular velocities once, and you'll get angular orientations. So PQR are body rates. So body rates. So body rates. And psi, theta, and phi are the inertial angles. These angles are defined with respect to inertial frame. Inertial frame is fixed. So if you recollect, in the last class, we derived two important equations. The first kinematic equation that we derived was the equation for translational kinematics. So basically, we said something like this, and I will rewrite this: Pn dot P E dot P D dot, which is nothing but X dot Y dot Z dot is equal to, and the velocity in X is U, velocity in Y is V, velocity in Z is W, is equal to a transformation matrix, which is R, that will and multiplied by U, V, W. You agree with me? Does everyone remember this equation? Yeah, the rotation matrix. And this rotation matrix, so this is inertial. So you can call this like IB, right? And I gave you that expression. The previous class, we did this transformation and we derived the equation. Do you want me to write that R matrix? So R matrix is cosine phi, cosine psi, minus cosine theta, sine phi, sine psi, all those terms. And then finally you have cosine theta, cosine phi, cosine theta, sine phi, sine theta. So this would be a 3x3 matrix. It's a long matrix, but we derived that using MATLAB and we actually looked at its application. Question? Yeah. Huh?
During swarming, how do helicopters know each other's position is?
Oh, there are different techniques when you do for swarming. So you can use a leader follower and all, but we will talk about swarming. Let's finish one helicopter or one quadcopter, and then we'll add one more quadcopter. Then we'll add one more quadcopter. All right. So the second important equation that I want you to remember is you have P Q R is equal to, and I derived this equation. This comes from the, remember Jacobian that we talked about, Jacobian of angular velocities. 0 cosine phi minus sine phi minus sine theta cosine theta sine theta, or sine phi, cosine theta, sine phi, cosine theta, cosine phi. So here you are going to have phi dot, then you are going to have theta dot, you are going to have psi dot. So this is how the second equation looks like. So these are the body angular rates, and these are inertial rates. And inertial rates are nothing but d by dt of inertial angles. And those inertial angles are roll, pitch, and yaw. These are the two equations that we spent a lot of time talking about. Now what we want to do is, we want to derive the equation of motion for the quadcopter. In the last class, I showed you at the end, there were 12 equations. And I said, those 12 equations are valid, whether it's a flying rock, whether it's a flying rocket, whether it's a flying saucer, whether it's a UFO, whatever it is. Now, what we are going to do is, we are going to go step by step and derive from the first principles the equations that are used for simulation of quadcopter. Please understand, if we write the equations of motion, those equations of motion are going to be nonlinear. And if you were to integrate, you cannot integrate those equations by the regular technique, like by hand or by formulae by the back of the book. You will have to use numerical integration to integrate those equations of motion. But you will notice that without any appropriate control, the quadcopter is going to be unstable, which means if you have that equation, if you have those 12 equations of motion and you integrate those numerically, you are going to get the results which would look weird. But that is what is the case, because the quadcopter is inherently unstable system. Unless you have a control input, you cannot have quadcopter in a controlled state. So what we are going to do is we are going to go step by step. And for this particular application, I'm going to make a lot of assumptions and try to simplify the geometry, try to simplify the equations. And as we go through this exercise again and again, we would actually make those equations more and more complex by relaxing the assumptions and then actually do the MATLAB simulations. So my hope is starting with these baby steps, we will develop a simple simulation, and then gradually we would keep on making it complex and then add visualization and so on and so forth. So here is the basic. You have a quadcopter. In the quadcopter, there are 4 motors, M1, say M2, M3, and M4. And the idea is the thrust given by motor is proportional to the speed square. That's what we derive. And there are electric brushless DC motors. You can use brush motors, but the modeling is similar. So you have electric motors. So let's start from the first principle. How would you derive the torque given by motors? So we are going to do modeling, math modeling. And once you understand the basic math, basic equations, MATLAB has built-in libraries and built-in Simulink blocks that you can actually drag and drop in your Simulink environment, and then you can actually plug in the values and then you can use those blocks. So for the DC motors, the torque given by DC motors is equal to KT multiplied by I minus I naught. This is the torque given by DC motors, where I is the input current and I naught is the no load current. Now, if you understand the basic principle of DC motors, you have something called as the back EMF. So the voltage that is supplied to the motor is the voltage drop across armature plus kV multiplied by omega, where kV is the constant that relates the back EMF to the angular speed. So kV is back EMF divided by RPM multiplied by RPM. That gives you the back EMF, and this is the voltage drop, and this is the supply voltage. Everyone understood this? These are the 2 important equations. Now the next equation is the power. DC power is voltage multiplied by the current. So V times I. So now please understand, from equation number 1, I can find out the value of I as torque, which is tau divided by KT plus I naught. And then what I can do is I can substitute this equation. I can substitute this equation here. And I can substitute this equation in here and find out the equation for power. And the equation for power, I would write it down. I'll just write this equation down, but you can verify T plus KT times IO, KT IO Rm plus tau Rm plus Kt Kv omega divided by Kt square. Now this is the actual model for power of the motor that comes from the voltage multiplied by current. Now what we are going to do is, in this first level approximation, I'm going to assume the motor resistance is very small. So this guy goes away. And then what happens is, this power equation sort of becomes proportional to tau plus Kt IO. So this becomes 0, this becomes 0. Kv omega divided by Kt. So this is the first level approximation. So you can actually assume the motor resistance Rm to be 0, and this gives you the equation for power. What this tells me is power is proportional to Kv by Kt times omega. So this is one expression, which means power drawn by the motor is proportional to speed. This is called as the power equation. Now the next equation is, what are the forces acting? So what are the forces? Now to find out the forces, please understand that you have a prop. Prop is generating some thrust. So you have some force, and the air surrounding the prop is displaced by certain amount. So basically, the power from the motor gets dissipated in the work done per time. So basically, the equation is the power that we derive multiplied by dt is equal to force multiplied by dx. So this equation, power from the motor multiplied by time is equal to the force multiplied by dx. And you will see that this equation is nothing but force dx by dt, which is nothing but force times velocity. So how does this equation come about in the case of props? So you have this prop that is attached to this motor, and we are going to analyze just one single motor. So there is some velocity Vh, and multiplied by the thrust is going to give you the power. So power is equal to thrust multiplied by Vh. So this is thrust, and this is the velocity of air. Now, next thing is, what we have to do is we have to use the equation for aerodynamics, and basically we are going to ignore other effects. So we are going to assume that there is no surrounding air disturbance, there is no turbulence, and this is a very simple assumption. So from momentum theory, this is the aerodynamics momentum theory. Thrust is equal to 2 times rho times a Vh square. So where rho is the density of the air, A is the area, and V is the velocity. And this comes from the aerodynamics. If you look at the momentum equation for the air, the thrust is equal to 2 times rho A V square, and which means Vh is equal to square root of T divided by 2 times rho times A. So now what we want to do is we want to equate these two equations. So we have an equation for power. Equation for power is T multiplied by VH, and basically we substitute this equation. So P multiplied by TH. We also have the equation for simple power equation. So you have this equation. So look at this equation, equation 1, equation 2, and equation 3. So we are going to equate equation 1, 2, and 3 and derive something like this. P, using the first equation, kV divided by kT multiplied by tau multiplied by omega. This is the fundamental equation of power that we derived, which is equal to kV k tau multiplied by the thrust divided by kT, because this is nothing but torque multiplied by omega, and that is equal to, now please understand, here it would be T times VH, so which is T times VH. T is the thrust. Equation for VH is square root of T divided by 2 rho A. So what we want to do is we want to simplify this equation, and I would encourage you to simplify, and at the end what you should get, do you want me to derive or can you simplify this equation? So let me just write this. kV k tau by kt omega is equal to T divided by square root of 2 rho A. That gives me kV k tau square root of 2 rho A omega divided by kt square is equal to T. So thrust, this is the important equation. What does that mean? Everything else except omega is constant. So which means T is equal to a constant K omega square. So now there are 4 motors. So total thrust will be summation of 1 to 4. So mi. So I can say that, and this thrust is going to be in the z direction. So I can write this down something like this is the force in the x, force in the y, and force in the z is omega I square multiplied by, so basically you would have k summation 1 to 4. So this equation would look like 0, 0, k1 omega 1 square plus k2 omega 2 square plus k3 omega 3 square plus k4 omega 4 square. And total thrust is going to be f of x, or I would say t of x, t of x, t of y, and t of z. There is no thrust in x and y. If you want to know what is x and y, this is the quadcopter, and say this is north, this is x, this is y, this is z. So there is thrust in the z direction. Everyone understood this? Now next part is, as this quadcopter is flying, the air is going to resist its motion. So as this quadcopter is flying, the air is going to resist its motion. So there will be some drag force from the air. So that drag force is approximated as, so drag force, and this is just an approximation. Drag force is Fd, which is Kd x dot, Kd y dot, Kd z dot. So you will have force in x direction, y direction, and z direction. So please understand that this drag force, the aircraft would have some velocity in x direction, which is x dot, velocity in y direction, y dot, velocity in z direction, z dot, or in our conventions, it is u, v, w. So that velocity multiplied by the coefficient of drag is going to give you the drag force that is given by the air as that quadcopter is going to move. Now this is an approximation. Many a times you can derive the drag forces in body coordinate system, or for simplicity x dot, y dot, z dot, you can derive the drag forces in inertial frame. So as a first approximation, I'm just going to say kd x dot, kd y dot, kd z dot. These are the inertial velocities. Please note, this is an approximation. So inertial velocities as an approximation. However, for actual analysis, you should be looking at the body velocities, because that is where the drag force is coming along. But at first level approximation, we would say x dot, y dot, and z dot are the inertial velocities. Next thing is torque. Now, torque comes from, again, the aerodynamic drag force. So Fd, which is the drag force acting on the prop. So please understand why this drag force come in the picture. So you have this prop. This prop is rotating through the air, and as this prop is rotating, there is going to be some drag force, which is nothing but the dynamic pressure multiplied by area multiplied by the coefficient of drag. So that is going to be 1/2 rho multiplied by a v square multiplied by cd. Now please understand, a is the reference area, and depending upon the prop dimension, depending upon the type of prop, the reference area would be different. V is the velocity at which the prop is going through the air. So the total torque, drag torque, is equal to 1/2 multiplied by the radius multiplied by the force, which is rho cd a v square, and v is the pitch line velocity of the prop. So this is the velocity which is dependent on angular speed. So finally your equation, I'll give you the equation, becomes r rho cd a omega r square, that can be simply written as b times omega square, because r is constant, rho is constant, cd is constant, and a is constant. So the drag torque, tau d, is equal to b multiplied by omega square. Now please understand that prop has some inertia. So in addition to the drag torque, there will be inertia torque, which is tau z is equal to b omega square plus I m multiplied by omega dot. So basically that is the torque tau, and b is basically assumed as the drag coefficient, and this equation is valid when omega is changing. If omega is not changing, if omega dot is equal to 0, then this expression can be approximated as B times omega square. So what I want to do in next class, I mean next lesson, or next part of the lesson, is find out the torques about the roll, torque about the pitch, and torque about the yaw. So let's start. So let's look at our quadcopter. So this is our quadcopter. This is our quadcopter. And then what I'm going to do is I'm going to call this 1, 2, 3, 4. This is my z axis. So basically this is my yaw. So torque in yaw direction is going to be B omega 1 square minus omega 2 square plus omega 1 square minus omega 4 square. I'm assuming omega 1 and omega 3, omega 1 and omega 3, they rotate in the clockwise direction, and omega 2 and omega 4 will rotate in counterclockwise direction. So what's going to happen is the torque given by rotor 1 and rotor 2 would cancel the torque given by rotor 3 and rotor 4. Everyone understood this? So this is the torque about z-axis. Now, next thing is I want to find out the torque in the roll direction. So I'm just going to assume maybe this is z. So let's see, I'll call this x. I call this y. So if I want to talk about roll is about x. So this is roll. So torque in the roll direction is equal to a constant L, which is the distance from here to here, which is same as distance from here to here. L multiplied by k omega 1 square minus k omega 3 square. So this equation is L k omega 1 square minus omega 3 square. This is the torque. Question?
So to change the direction of the quadcopter, do we just change omega 2 and omega 4 or vice versa?
So it totally depends upon when you say direction, do you want to change, you want it to go roll, pitch, or yaw. So depending upon that, we change. But let me derive the equation and it will be clear. Similarly, the torque in the theta direction, which is this is roll, this is pitch. So torque in the theta direction is going to be L k omega 2 square minus omega 4 square. So now I can write this equation down for the torques. So tau roll, tau pitch, and tau yaw is equal to L times k omega 1 minus omega 3 square L k omega 2 square minus omega 4 square, and B, remember B is the drag coefficient, omega 1 square minus omega 2 square plus omega 3 square, because omega 1 omega 3 are in the clockwise direction and omega 2 and omega 4 are in the counterclockwise direction. So this is the equation for torque. Next part, and this is super duper important. So I want everyone to pay close attention. So next part is equation of motion. And I'm going to repeat this once again for my own satisfaction. There are only two equations that you should remember from Newton's laws. So the equation is the rate of change of linear momentum is force. So rate of change of linear momentum d by dt of mv is equal to force. Do you agree with me? And rate of change of angular momentum is torque. Rate of change of angular momentum is torque. Now there is something that I want to clarify. So if you look at the very first equation, I'm pretty sure that all of you have seen this equation in high school. Do you agree with me? This is how it is start. So you start with this equation. Mass is going to remain constant. So you take mass outside, and then you have d by dt of v is equal to f. And that goes something like m times a is equal to f. You agree with me? This is how the equation is start. Force is equal to mass times acceleration. Now, at this point, I want you to understand a very, very important thing. This v is a vector. This v is a vector. And this requires a little bit discussion. And I'll tie this into what we discussed in last class. So this v is a vector, which means m, when I say m dv by dt is equal to f, that has a scalar component that needs to be differentiated, and it has a direction component, or it's at a direction that needs to be differentiated. Everyone understood this? But what you have studied so far is this dv by dt, or this v, is always expressed in the inertial coordinate. Please understand, this v is always expressed in the inertial coordinates. And in inertial coordinates, direction does not change because it's a fixed coordinate system. That's why dv by dt is approximated as a. You agree with me? However, if you think about this equation and think about what we studied in last class, v is a vector. Do you agree with me? So I should be writing this equation down. The right way to write this equation down is m multiplied by, say, if I have v, which is the scalar part of v, which is v dot, plus m multiplied by the direction part of v, and that could be that v could be in I direction, j direction, z or k direction. So I'm going to just, for the sake of discussion, I'm going to say v I dot is equal to f. Do you agree with me? But it, when we study the dynamics, nobody tells us that this equation is, because we take it for granted that this equation is derived in the inertial coordinate. That means that's why this I guy is 0, and your equation becomes force is equal to mass times acceleration. But please understand, you can write force is equal to mass times acceleration when the coordinate system is moving, but that is not how it is generally written. Everyone understood this? Now I want you to think about the second equation. D by dt is equal to I omega. I is the moment of inertia. Do you agree with me? Moment of inertia is actually, we assume to be constant for body, just like mass. So it comes out. But if I want to really differentiate this equation, I should be differentiating the magnitude of omega and the direction of omega. Do you agree with me? Just like what we did in last class. What does that mean? It means if I want to really differentiate this equation, I should be writing I omega dot plus I multiplied by omega cross omega is equal to T. Everyone understood this? The other way this can be written, and this is the famous Euler equation, plus omega cross I omega is equal to T. Remember this. And this is what we studied in last class, where I said I times omega is equal to H. So this is called as Euler equation. And the reason for that is angular momentum is a vector. It's not a scalar. Whenever you differentiate a vector, you have to differentiate its magnitude and you have to differentiate its direction. If direction is constant, then the derivative of direction becomes zero. But you cannot assume that will always be zero. So that is the equation that we should be focusing on. Okay, everyone understand? What is with negative? Cross product negative?
I omega cross omega.
Oh, okay. Don't worry about. Okay, let me answer this question in just a second. Omega is a vector. Omega is a vector. What that means? It has omega x in r direction plus omega y in j direction plus omega z in k direction. I is, remember the inertial tensor that we talked about? It's a 3x3 matrix which has ixx, iyy, izz, and then it has cross products of terms. That's what we discussed in last class. Everyone understood this? Now I'm gonna make simplifying assumptions. So consider that I have a quadcopter and this is its center of gravity. I'm going to take the moments about the center of gravity. And when I take the moments about the center of gravity, the product of inertia terms, they cancel each other out. So you get zeros and you just get principal moments of inertia. So this is the equation that I'm gonna play with and derive the differential equation of motion. But before we go to angular velocity, let me conclude what we have over here. So the equation of motion in translation, the exact same equation that we derived in last class, is written as mx double dot is equal to the gravity or the weight will always act in z direction. So there is no component of weight in x direction, no component of a weight in y direction, but it has the gravitational, the weight mass multiplied by gravity, which is the weight in the z direction. Plus, you have some thrust that is coming, that is actually given. Remember the equation for thrust that we derived earlier, T1, T2, T3. So these equations for thrust, that equation of thrust is in the aircraft body frame. So I need to use the rotation transformation that would take me from body to inertial, because this is in the inertial frame. This is in the inertial frame. And this is the thrust in body frame. plus I have the drag force, and this drag force I'm approximating in inertial frame. So this is an inertial frame. Are you with me? Yeah.
Why is mg negative if z is down?
Oh, yeah, you are right. Mg you can treat it positive. Yes. Okay. Any other questions from online students or in-person students? So please understand, this equation is nothing but it is mx dot. I just need to clarify. It would be mx double dot my double dot mz double dot. So basically, it's a vector equation. It has 3 rows. Everyone understood this? So summation of forces in x direction, summation of forces in y direction, and summation of forces in z direction. Everyone understood this? Okay, now comes the most important part of today's lessons. So super important. And I'm going to rewrite, I'm going to write this again. So the first part is, this is what I said. Rate of change of angular momentum is equal to torque. So the angular momentum has a sort of a scale that needs to be differentiated. Angular momentum has a direction that needs to be differentiated. So when I do that differentiation or vector differentiation, I get this equation: I omega dot plus omega cross I omega is equal to T. This is called as Euler's equation. Now I want you to realize what's happening here. This I is Ixx 0 0 0 Iyy 0 0 0 Izz. You agree with me? Omega dot is omega x dot omega y dot omega z dot plus. Now here comes the problem. This omega is a vector. So what does it look like? It looks like omega xi plus omega y j plus omega z k. And then there is a cross product. But this cross product also is a little bit weird. So I have Ixx 0 0. Yeah.
So why is there a plus? If it's in different, like, so that's just 1 unit.
What and 1 minute?
Is omega one by one vector? Sorry, 1 by 1 matrix.
No. So right now, what I'm saying is, just wait. It will work out. This is a vector in 3 dimensions, right? This is a vector. Let me just write this down, and when I will solve it with a cross product, and then it will make sense. Right now, it doesn't come across like equation that has 3 rows. I understand, but bear with me for a second. Izz. And in addition to that, what I have here is I have omega, which is omega x I omega y j plus omega y j plus omega z k. So something like that. I have this equation, and I will evaluate this equation separately. And before I evaluate, there is something else I need to do. So please try to understand. This equation is something like this. And after we perform this complicated cross product multiplication, we should get some equations. But before that, there is an important step. This equation is I omega dot plus omega cross I omega is equal to tau. What I'm going to do is I'm going to take omega dot on one side, omega dot. I'm going to take tau minus omega cross I omega and then use I inverse. So this is the equation that actually I would like to derive, where I have the rate of change of angular velocity, and this equation is angular acceleration. This is the torque, and this is the inverse of inertia matrix of I. Now, if my I is Ixx 0 0 0 Iyy 0 0 0 Izz, what would be the inverse of this guy? Think about like it is an identity matrix. What is the inverse of an identity matrix? 1 divided by identity matrix. If I have a diagonal matrix, what is the inverse of a diagonal matrix? Inverse of the diagonal elements, right? Are you with me? So this equation inverse, I inverse, becomes 1 divided by Ixx 0 0 1 divided by Iyy 0 0 0 1 divided by Izz. Are you with me so far? Okay, so we found out I inverse. Any questions about tau? Tau is tau x I, tau y j, tau z k. Any questions about tau? So this omega dot is omega x dot, omega y dot, omega z dot. So omega xi, omega yj, omega zk. So we figured out what the first term is. We figured out what the second term is. We figured out what the third term is. Now this is the term that we need to really look at. Now this term is what? Omega cross I omega. So first and foremost, where is this term coming from? This term is coming from because the direction of angular velocity is changing. Are you with me so far? So angular velocity is a vector. The magnitude of angular velocity is changing, but the direction of angular velocity is also changing. This is the derivative of that direction. Everyone understood this? This is super important. So now how do I find this out? This is a cross product between two terms. Now I, and I'm gonna make a simple assumption. I is a scalar quantity. It is just bunch of numbers. So what I could do is actually I would write this equation down as something like I j k omega x omega y omega z. This guy comes from here. And I xx omega x I y omega y I z omega z. And to find this cross product, I need to evaluate this determinant. How would I evaluate this determinant? I omega y, so I z omega z omega y minus I y omega y omega z minus j omega x I z omega z minus I so so let me see, I z z omega x omega z, then I xx omega x omega z plus k omega x I y omega y minus I xx omega x omega y. And now please look at the symmetry. Omega z omega y omega z omega x omega z omega x omega z omega x omega y omega x omega y. So this equation can be written as I z z minus I y omega y omega z minus j I z z minus I xx omega x omega z and k I y minus I xx omega x omega y. Are you with me so far? Everyone understood this? This is super duper important. So this product with all this mathematical jugglery gives me this guy. Now what I do is I plug in these values in the previous equation, and this equation becomes omega x dot omega y dot omega z dot is equal to tau phi tau theta tau psi Ixx inverse Iyy inverse Izz inverse minus Iyy minus Izz divided by Ixx omega z omega y Izz Ixx Iyy omega x omega z Ixx minus Iyy Izz omega x omega y. And we have derived the equations of motion for quadcopter. So next part is using MATLAB to simulate the quadcopter. And clearly, when you simulate the quadcopter without control, it's going to be unstable. Because if you have a quadcopter, there is no control, it's like a rock. You can't expect rock to be in stable flight. So how would you simulate these equations using MATLAB? And we will do that in next class, or if you just want to try, I've already uploaded the quadcopter simulation .rar. There is a simulation function. So we have these equations. So you would convert those into first order equations, something like this: 0, 0, 0, 0 g plus 1 divided by m r tb plus 1 divided by m fd. And I'm just going to write this equation in a short form. X3 dot is equal to 1, 0, 0, 0 cosine phi minus sine phi minus sine phi cosine theta sine theta sine phi cosine theta cosine phi, the inverse multiplied by x4, and the last equation is x4 dot is equal to the equation that we just derived, tau phi tau theta ixx inverse iyy inverse izz inverse minus iyy minus izz divided by ixx omega y omega z izz minus ixx iyy omega x omega y omega z, and the last equation is ixx minus iyy izz omega x omega y. Now what are these x's and what are these? So basically this x is pn dot pe dot pd dot or x dot y dot z dot. X2 is the accelerations, x3 is nothing but phi dot theta dot psi dot, and x4 is nothing but p q r, the body, and then omega x omega y omega z are the, so x dot here becomes p dot q dot r dot is equal to this equation. So please try to understand, these are three equations, these are three equations, these are three equations, and these are three equations. So these 12 equations of motion will simulate your quadcopter. Now what happens to the control? Now for that, I want you to think about where we have control. The control, we have only control of motor speeds. So which means by changing the speeds W1, omega 1, omega 2, omega 3, omega 4, we can manipulate TB. We can manipulate TC, T psi, and T theta. Do you agree with me? That is the control that we have. So when we simulate these equations in next class, you would realize that unless you have proper control, if you have some sort of PID control or sliding mode control or some other nonlinear control, the quadcopter equation of motion, these are the quadcopter equation of motion in 3 dimensions. And then what we can do is we can actually look at proportional control, proportional plus derivative, and proportional plus derivative plus integral type of control to stabilize this quadcopter motion. And I'm going to stop here today, but I just want to tell you that this lesson, in my personal opinion, is the most important lesson in robotics too, because this is where you understand the simulation. Once you have the differential equation of motion, the next part is just tuning or changing the values of t, changing the values of tau based on some type of control algorithm, and then make sure that the quadcopter is in stable hover, quadcopter is able to follow a particular path, and so on and so forth. Before I stop, any questions on the material that we discussed today? You have seen similar material in aerial robotics. Only thing is, I don't think that they were derived, the equations were derived from the very first principles. Are they derived from the? They are not derived from the first principles. But once you understand this, you can derive equation for any flying robot. I'm going to stop here.